Remember those times where you got so annoyed with school that you started counting the number of years or months or even days until you didn't have to do this anymore? And then your parents hit you with that, remember, learning is a lifelong process. You probably grumbled and rolled your eyes.
But actually, a phenomenon called neuroplasticity allows your brain to adapt its structure and function in response to experience, making learning literally a lifelong process. Crazy, right? But what might be crazier is that your parents had a point. Here's an example. Let's say you're learning a new language. While the words may seem meaningless at first, through practice, your brain forms connections between the words and their meanings. Over time, the connections get stronger and stronger until Hiro won't call your Google Translate, rather a dog. Before we go deeper, let's understand how a brain cell or a neuron works.
Neurons communicate through electrical impulses called action potentials. Dendrites receive signals that are used to create action potentials, which are generated when sodium ions flow into the cell and change the relatively negative resting membrane potential to positive. Then, the action potentials are transmitted through the axon to axon terminals and synapses.
At birth, humans have around 2,500 synapses, which are junctions between neurons where neurotransmitters are released. Until we're around 3, neurons rapidly overproduce synapses. But after this time, as more sensory information is accumulated, synapses start to strengthen or weaken, and unused connections are eliminated through synaptic pruning. This synaptic plasticity occurs through potentiation and differentiation.
During potentiation, synaptic connections strengthen. This can be done through more frequent action potentials or an increase in receptors and synaptic sensitivity. In long-term potentiation, the neurotransmitter glutamate is released into the NMDA and AMPA receptors. A low level of glutamate activates the AMPA receptor, but not the NMDA receptor, which is blocked by a magnesium ion. Through frequent action potentials, the more stimulated AMPA receptors depolarize the neuron, which removes the magnesium ions. This allows calcium ions to flow through the NMDA receptor and activate kinase to help generate more AMPA receptors, which renders the synapses more sensitive to neurotransmitters. Now, during depression, synaptic connections weaken through less frequent action potentials or a decrease in receptors and synaptic sensitivity. In long-term depression, low stimulation of AMPA receptors is not enough to remove the magnesium ion and the NMDA receptor. However, a few calcium ions still enter, and the lower level activates phosphatases to facilitate removal of AMPA receptors, weakening the synapse.
Through plasticity, the brain can also change its function in multiple ways. For example, if a person is born blind, their sense of touch can be redirected to their visual cortex. From strengthening learning and memory to designing new brain trauma recovery therapies, scientists are researching how neuroplasticity can help treat Alzheimer's, strokes, and more. So, understanding neuroplasticity has many beneficial implications, but above all, it teaches you school never